Hi, my name is Christopher Schulte, and today we'll be talking about lab number 5 with the topic of motion of an object using energy principles. The purpose of the lab is to observe the motion of a falling object that is dropped from rest straight downward using energy principles. Then we will generalize this model to any object dropped from rest. The goal of the lab is to utilize a tracking software to create observed position versus time graph of the falling object. Then, utilizing a computational model, we will create a predicted position versus time graph of the motion of the object, and then predict its final velocity based upon energy principles. Finally, we will compare the observed position versus time graph with the observed final velocity and the predicted position versus time graph with the predicted final velocity. Newton's second law relates the net interaction between the system and surroundings to the observed motion or changes in momentum of the system. From this, we can derive the position and velocity update formulas. Also, we utilize the energy principle and its relevant equations, and this states that the initial mechanical energy of a system equals the final mechanical energy of a system where no work is done by non-conservative forces. Also, we know that energy is neither created nor destroyed, but rather transferred. In this lab, we see kinetic energy and gravitational potential energy. Overview of results. The system included the pencil pouch and the Earth, while the surroundings had nothing. Results. As predicted, the tracked y position of the mass closely mirrored the position versus time graph produced by the computational model, and both models have similar final velocities. However, there are still somewhat noticeable differences in these graphs, likely as a result of experimental error or imprecise measurement of the mass's position while falling. Data and analysis. Here you see the observed motion from their tracker. The mass was 0.184 kilograms, the initial position was 1.500 meters, and the initial velocity of the pencil pouch was 0 since it was dropped from rest. Here we see the produced graph showing the y position data over time of the pencil pouch, and the value of g is 9.8 meters per second squared near the surface of the Earth. Here we see our computational model, or the predicted motion. For our initial conditions, we see the mass of the object is 0.184 kilograms, and we also have the initial position and velocity vectors. The value of g is 9.8, and b is equivalent to 0, and this is the proportionality constant for the magnitude of drag. However, there is no drag in this model. In our while loop, we see the net force calculation, which is used via Newton's second law. And from that, we can also derive the velocity and position update formulas at the end of each iteration. Net force equals mass times acceleration, or in this instance, negative mg. This calculation came out to negative 1.8032 newtons. Some equations and physics principles used included Newton's second law, and we used the velocity and position update formulas in each iteration of the loop, and we also know that gravity near the surface of the Earth is negative mg in the y component. Additional principles included kinetic energy, which is 1/2 mv squared. We also used gravitational potential energy, which states that it is equivalent to mg delta y, or the height above the ground in this case. Weight is constant as the object is falling, while resistance due to the drag force is dependent on the magnitude of the square velocity. According to the energy principle, we know that energy is neither created nor destroyed. Comparing our graphs and energy changes, we see that all models have the same initial position, and the time taken to reach the ground is much smaller in the computational model compared to the observed model. All models show that the velocity increases in magnitude as time progresses, as evidenced by the steepening slope, and all models start with only gravitational potential energy, and we know this because the initial velocity is 0 meters per second. Potential energy is then converted completely into kinetic energy, except for in the model with drag. The predicted versus actual final velocities are similar, however they have slight differences. The observed velocity was used by calculating the change in displacement over change's time and the time interval immediately before hitting the ground. This was calculated to be negative 5.20 meters per second. For the predicted velocity model, we know that delta equals 0, or the summation of initial energies equals the summation of final energies. Therefore, the initial gravitational potential energy equals the final kinetic energy. And then when setting these two equal to each other, we know that the final velocity is equal to the square root of 2gh, or negative 5.42 meters per second. Conclusions. Some main ideas and key takeaways show the relationship between Newton's second law, the energy principle, and the forces at hand in this lab. We know that energy is neither created nor destroyed, and that in a closed system, the total energy equals 0 at all times. With this, we can calculate the final velocity of the objects as they reach the ground, and predict the motion utilizing Newton's second law and these position and velocity update formulas. Error analysis. A possible source of error is inaccurate data collected from the tracking software. If the video was captured from a slight angle or the video quality was not adequate, the tracked position could differentiate from the actual position of the falling pencil pouch. Also, it is possible that small external forces such as drag impacted the behavior of the system. This would account for why final kinetic energy is not equal to the initial potential energy of the system, and the final velocity would be slightly different than initially calculated. What if? If you dropped a 10-pound bowling ball, a paper clip, and a pencil pouch next to each other, all three would have the same final velocity. if they are dropped from the same height. As seen in the calculations below, the mass of the dropped object has no influence on the final velocity of the object. This is because when setting the initial gravitational potential energy equal to final kinetic energy, the mass cancels out and the value for the final velocity equals the square root of 2gh. What does it mean? Drag force is a non-conservative force, meaning the work done by it is path-dependent, so under friction it produces heat and thus does not conserve mechanical energy. Since the initial gravitational potential energy is now converted into both kinetic energy and thermal energy, the final velocity predicted by the computational model would be higher